Okay, now we're on the next step. This graph is just getting more and more ridiculous, but hopefully I can explain it really good. A few things here I wanted to point out. One in green, one in green. One in green to two in orange being right here. These are evolution processes. These are the processes where the star evolves and it changes significantly due to evolutionary forces. After about this right here, this stage, when the star begins dying, I call this the terminal phase. This is a terminal phase curve, and it marks the end of evolution and start of disintegration. Meaning the object doesn't actually evolve past this stage. What it actually does is just start to fall apart and get ripped away by the hotter radiation of outer space, the UV radiation, the X-ray, the gamma rays, and impacts and all that stuff. So we're going to use Venus as the example. Venus is sitting right about there, and it sits on a phase curve. But keep in mind, it does flatten out right here for dead objects, but I think we can change that up now. There's still dead moons right there, but you see that little black line right here? You can erase that, and all those little tiny dots should go down here as well. And basically you have Venus, it disintegrates and loses mass and loses mass. Remember, mass is on the left-hand side. Loses mass, loses mass, loses mass. And there are phase curves for the disintegration processes. So some stars can disintegrate slowly up here, and some stars can disintegrate fast down here. So with Venus, it starts right there, goes down, 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 down. About 300 billion years I have right there. Venus should eventually be broken up into medium and large asteroids, which then enter in the surface and atmospheres of much younger stars. And then the leftover remains of Venus. Keep on going, keep on going. And Venus at about 1 trillion years would be broken up into small asteroids by then, and they're scattered about the galaxy. And then Venus's remains continue on, continue on, continue on. Eventually at about, what would that be? About 50 to 60 trillion years, Venus will finally end up as just gas and dust particles, which then wander about outer space, and Venus's remains will be all over the galaxy and all over other galaxies and have already been recycled into younger, hotter stars. And that is very, very interesting because it means that this object, I have another little one here. This was tumbled, that's why it's a little bit shinier. These two objects that sit down here possibly not only sit down here with meteoroids and meteorites over on this side of the diagram, but they possibly sit way the hell over here too. Which means these two objects could not only possibly be, up to 65 billion years old, but could possibly be 300 billion, a trillion, 10 trillion, or even broken up bits of ancient dead stars well in excess of 80 trillion to maybe even 100 trillion years old. And what that means is that this material should be all stable nucleons. So iron 56, I believe iron 57, iron 58, I believe those are the stable nucleons. There shouldn't be any radioactivity left in these objects at all. These objects should be completely inert. And that will be for a future paper, because what it means is that the younger object you have down here, objects like this, if there's more youth to it, there's more radioactive material. And as that radioactive material decays, of course, determined by its half-life, the objects that are really, really, really old shouldn't have any at all radioactivity coming from them, because even with a half-life for uranium, say at about, what was uranium-238? I'll write this down. U-238's half-life is, I believe, what's that, 4.4 something billion years? That means if you take a certain amount of uranium, say 100 grams of it, in 4.4 billion years, that 100 grams of U-238 will become 500 grams. And then another 4.4 billion years, that 500 grams of U-238 will be 250 grams. So its half-life, how much that material decays over time, given in half. So you have a full amount, half-life, that means you left with that amount, half-life, left with that amount, half-life again, all the way down the line. And even with that, with a half-life of 4.4 billion years, an object that's, say, 1 trillion years old shouldn't have any radioactive uranium in it whatsoever. It shouldn't have any U-238 or any other long-lived isotopes of any element, for that matter, because all of it should have decayed. What that possibly means is, since if this is completely dead, and looking at this diagram for a Venus or any other object that came before Earth a long, long time ago, it could mean that these objects, of course, again said it, could be trillions, tens of trillions of years old. I mean, unbelievably old, like so old it just, you can't even comprehend it. Fortunately, that's why I'm making these diagrams. And this disintegration curve is up for, these disintegration curves are up for revision, as well as all this other material is up for revision. But this is the direction I'm headed, and I went ahead and stretched out the small asteroids and meteoroids, the gas and dust, all the way over here. And also Earth, the transformation curve will continue on, and it'll become like Venus, which then will follow in Venus's tracks and disintegrate. Now, of course, this can all change too, because if Venus somehow is ejected from the sun when the sun loses its mass and evolves itself, takes up orbit around a younger, hotter host, then it will disintegrate a lot faster. So Venus could probably just go right here a little bit and then just fall down here because it's been, because it's being disintegrated. And then, that'll be that. It won't go all the way down here. This is just representation. But still, even if Venus is down there, goes like this and it goes down here, it'll still be in excess of 65 billion years old. And the material will then, be recycled, obviously. There's that, and another idea that I had here. I have to account for the mass of the object, and it's what's called a escape velocity, because certain objects, the escape velocity for certain elements, such as Earth, like say water is at 300 Kelvin, something like that, will escape a certain sized object. So, if water can escape an object that's this mass and below, then it means the ocean world stage should be a little bit higher. But then again, I still have to work out a lot of that stuff. And a lot of these bottom phase curves, these are up for revision as well. They're just representative, and I use them to see if I could draw conclusions that I haven't concluded before. This is all brand new even to me. Even though it's been over 7 years, all this material is still new, and there's so many different pieces of the puzzle that I have to put together. It's taking a lot of time. All right, and hopefully this helps you out, Baz. If you have any questions, of course, feel free to ask. I'll be here all day. Later.